so much. For my presentation, I'm going to present the system that we are implementing in Metro Vancouver that has gone online just a few months, but has been in development for a few years. The good thing is we had a few presentations before that, especially from Curtis, that explained the problems in Metro Vancouver, so he made my job a bit easy. I think you all know our company. What we try to do is come up with new innovative ways to deal with the problem. So we have a very strong research division. And during my presentation, I want to highlight some of the work we've done, and I want to share with you some of the research we're doing into future monitoring technologies like nanofibers and things like that, that we're trying to kind of push the boundaries of what we can detect in terms of pollutants and odors. So as we heard before, the two wastewater treatment plants that we focused on were Lulu and Ayo. These were the ones that had the biggest complaints, and they were also situated in a way that their complaints were not necessarily driven by them, but sometimes by other industries around them. So the objective was not only to figure out what complaints are coming from the plant, what complaints are caused by what process in the plant, and also to some extent distinguish those from other processes, rendering plants and waste, there's a wood processing plant, pulp and paper or something like that. So we were trying to distinguish these kind of odors. So you have got a pretty good understanding of the kind of monitoring program that was taking place. It started in 2012. We started with Metro Vancouver, providing equipment and expertise to set up the program that Curtis talked about. So they've been doing that for now 5 years, and they have been taking measurements from the sources, as you heard, from the community, and putting it together to understand how the process is affecting the odor complaints. So they would have these responses to the complaints where they would go out and make measurements and come back and validate it with dispersion model. Now, the odor patrol that was directed for about 5 years that they were going around collected a lot of useful data and kind of validated this form of monitoring. It worked really well. All the complaints could be traced back to something that happened at the plant. The complaints would also be distinguished from like what Curtis showed, if it was a digester or something like that. And this program actually really works well and captures everything. But there is some shortfalls, and there is some places for improvement where we can have continuous monitoring. And there's always a need for continuous monitoring. For one thing, doing it manually is kind of expensive. Metro Vancouver invests very heavily into odor nuisance and odor complaint management, but that's kind of rare, at least where we're from, like Toronto and other places. They're not as willing to spend so much money on the monitoring campaign. The second thing is you may have monthly or even weekly monitoring, with some person walking around making measurements, but sometimes the emissions change faster. You have complaints that are due to weather that are changing much faster, and it's not always feasible to be available, to be deployed so quickly, and to do that much monitoring. So we wanted to have something that would monitor 24 hours a day. Now, odor monitoring is a really difficult problem. And the main problem is because you're monitoring not a physical thing, but a psychological response to a physical thing. So for example, I want to monitor H2S. That's a physical thing. There are molecules, and I'm sure if I can somehow measure them, I will be correct. But when you're talking about odor, if there's no people, there's no odors. So I'm not monitoring H2S, I'm not monitoring my captains, I'm monitoring the response of the community. And that becomes a really difficult case. Secondly, the things that we have to monitor, let's say even the pollutants, we just want to monitor odor pollutants. some of them are so low, the detection thresholds are in the parts per trillion, that it's really hard to measure by any analytical means, not just if you want to use low cost or high cost, and even in a laboratory. For some things, like in a rendering plant, to really capture all the pollutants that cause it, they're even below parts per trillion. So there just isn't any analytical solutions available to measure those at those levels, never mind continuously. The second thing is, as I mentioned, the machines are measuring pollutants, and how do we bridge the gap between those pollutants and what we think humans should respond. The third problem they wanted to do was to have source identification. So they wanted to know, is it wastewater treatment odor? Is it pulp and paper? Is it rendering? What is the source of this odor? In this case, we're not going within the plant. So what Curtis was talking about, we're not trying to distinguish the digester from the solid or something like that. We are focusing on plant or not plant, but it could be expanded later to be picking up what the actual source is. And the fourth one was just placing instruments wherever you want. It's easy to see on a Google map or put it here or there. But sometimes, especially when the public, it's not the case here, but when the public is really against the industry, like we had this project in Colorado, and any instrument we would put close to the receptors would be destroyed if we, even with casing, even putting it in a dog case, dog shelter, it would still be destroyed. So sometimes there is some challenges in dealing with the public when you're going out and trying to place instruments, trying to do odor control, things like that. So we tried two different approaches here. There is one approach which would be to figure out all the pollutants and add them up and get one odor concentration. And the other one is to use a tracer test, saying I'm not going to be able to measure all the different pollutants I have, but if I can just measure methane, for example, for a landfill, it would correlate well with the odor. Now that graph doesn't represent a typical landfill, but it's kind of like more exponential than that. But still, if you have more methane, you have more odors. But for some things, it's not so easy to just pick a tracer. And the tracer has to be properly picked. H2S is used as a tracer for wastewater treatment plant for the very basic reason it's easy to measure. It's easier to measure than anything else. If I say pick DMDS, and it's a good correlator, pick it at PPT level. To do that kind of analysis would be really expensive. We wouldn't have handheld analyzers and data loggers that can drop into the sewer. So H2S has become the standard for measuring performance. And at the same time, it's not really a good tracer. It doesn't correlate, no matter how much, at least from our point of view, and what we have found, is the correlation breaks down very quickly. It's, yeah, you can pick some things, like if it goes up, probably there's more odor, but that's about it. You can't come up with an odor concentration based on just an H2S reading. So in the first approach, trying to capture all the different pollutants and putting it together, we went with the GC, similar to what's inside that shelter. And this is supplied by Chromatotech, they are here as well. And it's a GC, gas chromatography, but it's not GCMS, it's a GC with a wet cell. It only picks up sulfur compounds. We are looking more at the inlet kind of odors in this case, so it would be more sulfur compounds. It won't really be that useful at the end of the process, where you have more sludge and it's more VOC based. But for the beginning, we think most of the odors are going to be sulfur compounds. So this GC can go to PPT level of all those pollutants. It takes measurement every 20 minutes. And will give you all those pollutants individually. So it's actually separating it. And you are sure what you're measuring as DMDS or DMS is actually what really is there. Now, we use a hybrid approach. having just the analyzers on the fence line would not be enough. Most of the time we would just read 0. What we wanted is to also directly measure the sources. So we're using Sentinel, which is our own equipment that we manufacture. And here, these are using different kind of technologies, not GC. You're not going to get DMBS and all those things separated, but you will get H2S, for example, VOC, it says VOC, VOC, methane, ammonia. These are the ones we selected in this case, not because we expected a high amount of VOCs and ammonia from some of the sources, but because we thought it would be a good way to distinguish some odors from others. And in this case, we're not looking for ppb levels, although this instrument does go down to that. We are looking more at the source, so we're installing it above the aeration tank, above things like that. In the inlet work, we are pulling directly from the inlets, screen room, things like that. So we're measuring the fluctuation within the source and trying to get, I think every 2 minutes, a data point. In this equipment, there is a sample pump, sensors, and what we found was very useful is to have a decontamination. What we found is when you're above the aeration tank and you're trying to take measurements, a lot of times you're measuring the contamination within the system. So here we implemented an ozone generating device within the system that is flushing out all the lines, and this was the result of the work that was done in Metro. But once we have this data, it still doesn't tell us. We don't want to model H2S, we don't want to model VOCs, we wanted to model odors. And we wanted to kind of follow the same thing that Metro Vancouver was doing, as well as Curtis and his group were doing. So we want to have odor units that we can correlate back to the data that we have for 5 years. So we use a deep learning algorithm. It's actually a Google-based algorithm that they released. And it takes the sensory readings, so that 5 years of data that we had, the continuous work that is being done by WSE, all the readings they take go into this kind of large data mining algorithm. And our sensor values go into it. So the algorithm is, what the point of it is, it's going to try to correlate the odor concentration that they're measuring from each source with what we measure chemically. And because we have a lot of data points over years and years, well, the previous data we can't really use because we didn't have the sensors there, but the last year or so that WSB is doing the work, we have that data, and we have a lot of data to be able to start learning from that and correlating the two together. So we feed all that data in. In addition, we feed it some process parameters such as temperature, humidity, ambient humidity, and it can take more than that. We really haven't done that, but it can be more of the process as well. And then for the odor source identification, we use a fuzzy logic algorithm. So it goes based on wind direction and based on the sensors that are more picking up pollutants, and it gives us sort of plant odor or not plant odor or plant odor and rendering plant, something like this. I won't really go into the details of the fuzzy logic, but if you want, you can visit us later and I can talk to you about it. This feature of it is kind of more difficult than even the odor concentration. And the main problem is that sometimes these two odors combined, if they were separated and unique, like when we were doing it in the lab, it works perfect. But when you go out into the field and then you have a little bit of that and a little bit of this, kind of the system has a hard time distinguishing that, like it doesn't tell you 50% you, 50% somebody else. It just kind of goes probably you, right? Like, so this is the part that needs, in my opinion, a lot more work to become more robust to the synergy of the odors. The data, so we did two kinds of dispersion models. First is the one that has been done by Metro Vancouver before, and WSP is continuing. So this is kind of like a static dispersion model. We run it based on emission factors that are measured and not changing. And we use this to place our boundary level monitors. We use it to determine the initial conditions of the live model we want to run. So here's where we put the equipment. You have one sentinel above the aeration tanks, and above the clarifiers, another one, and there's one by a sensitive receptor because he was the main, well, this guy. The whole objective is just to keep this guy, one guy on. So we put one right in front of his house. The GC location is there, it's not on. And then we have a web base which we call Total Odor Management. And all that information is kind of going in there, and that's the interface to the user. So the weather station, the historical data collected by the WSP and Metro Vancouver, Sentinel, GCs, and even complaint data are coming in. And the Total Odor Management's job is to validate the complaints, run the dispersion model to see what levels things were happening. It back calculates emission from sources that it didn't have, like Sentinels are measuring 2 different sources, but other sources that it's not being measured, it back calculates those to see if it can determine if problems exist, for example, biofilter breakthrough or something like that. And it displays all that graphically for the control room, so they can see, okay, today the plume is hitting the people, and the complaints have gone up, and there are valid complaints, things like that. We also, it is a sort of a community outreach, let's say, or a community way of message board, where we can warn the community of all the issues that are going to happen, and also they can see when they complain. In Metro Vancouver's case, they didn't open this feature, but they would be able to see if something is going on at the plant, for example, the biotreatment filter is under maintenance or something like this. This is one of the screens that you can see here. And you see this live kind of model as you log in, and it updates every few minutes based on emissions that are being measured by Sentinel, and every 20 minutes by the GC ones. The complaint record and validation was one of the main issues, because it takes a lot of time, as probably Curtis can tell you, to validate those complaints when you're running the model manually every time. These are not Metro Vancouver data, so these are just from a site in Norway, because we don't have permission to share them, but you can get kind of these kind of graphs of red dots being your odors that were complaints and valid, the green ones not yours, and yellow that might have been. That's the part of the fuzzy logic that is kind of like contributing it to maybe. We use it a lot also for forecasting, so that's part of the process improvement. So if it forecasts into the future, it sees the emissions are rising from the sources, it sees that the wind directions are going towards, and the model shows a big impact, it will draw a sad face, that face. And if things are going well, it will draw a green face. And the point of it is not really to know when complaints are coming, it's to schedule maintenance work or deliveries or whatever you have to do to take sludge out at certain times. And you can kind of start to get some trending of, if we do that work at this time, there is less chance of the odor complaint. So, to summarize, I think continuous monitoring is a very difficult case, but it is a necessary part of the odor management plan. Without monitoring of one kind or another, either going in a control or with some electronic help, it is difficult to tell if what you're doing is helping or not, or what part of the process needs improvement. Now, existing sensing technology is there. There's a lot of developments in machine learning that can help bridge the gap between human experience and what the machines are detecting. It's not, of course, finalized. There's a lot more work to be done, especially with source identification. but it is a good beginning, and I think it's starting to show some good results. But there is a lot of work to be done, especially in sensing, and this is where we're putting a lot of our money and efforts into new technologies, not using just chemical sensors. We don't really use too much mass sensors, but electrochemical and photoionization. We're going a little bit beyond that, trying to get miniaturized tunable laser diodes. We work with a company that does nanofibers where they are really replicating like a human nose, and miniaturizing GC to try to separate those pollutants and overcome some of the issues of electromechanical sensors. There's a lot of new technologies, and it's a very exciting field, so I hope next time I see you, I can present to you one of these as being a successfully implemented technology. Thank you so much.